All right, I think we're ready to start. People online, if you can hear me, please say something.
Good
Good morning.
All right, great. So we are ready to go. Today, we are going to continue talking about visually identifying different types of curved functions. So polynomial functions are the thing we've been talking about. So an x squared something, an x cubed something, x to the exponent 4 or 5 or whatever. So a bit more about that. We got through about half of that last time. We talked about turning points and we started talking about zeros. So we'll do a bit more with that today. And then a bit more with recognizing maximums, minimums, these intervals of increase or decrease. And then some things that we can know from the leading term of polynomial, the thing with the biggest exponent. And then that will get us almost ready to do the calculus stuff. We'll just need limits afterward. Okay, so from last time, we talked about this thing, this kind of graph. Which was the points that we talked about that was the most important on this graph? If you're the person who is like running this business, what point do you care about most? So when our, sorry, one second, let me mute the sound of people joining. Okay. So this point where Q is about 12, then we get this point here. It's the maximum. That's the largest, the highest possible total revenue. That sounds pretty good if we're running a business, the most amount of money that we could earn. How do we identify that point mathematically? If we have a graph, we can look and see it's about 12. How can we know exactly where it is?
The slope is 0.
Okay, where the slope is 0. So the highest point, if we draw a tangent line there, that tangent line will be perfectly flat. That flat line has a slope of 0. So if we have a tool to figure out slopes, which is exactly what calculus is, we can find out exactly where that highest point is. So that was the one. And this one here, a little more complicated. Which is the point that is best? If you are a person running a business, this is your total cost curve. Okay, so at this point, we have made and sold 0 objects, and we've paid a whole bunch of money for the fixed costs. 50 or 60 here, roughly, okay. Why is this a nice point? We don't know about break-even point if we need the total revenue, but just looking at the cost curve, what's nice about this? Okay, so it's not the lowest possible total cost. That would obviously be here, but that is when we don't sell anything, so we'd have no revenue. What is nice about this point is it's sort of the most efficient. As we make and sell more things, our production system gets more efficient. This is the lowest average per unit cost. If we take the total cost here that we have, and we are dividing it by how many things that we make, spreading it out, the cost amongst each item, it's the lowest per unit cost. So that's where we get the most efficient. If we go beyond this, we get less efficient because our factory or whatever is too big and our average cost per item starts going up. So it's the most efficient point. And how can we identify that one mathematically? Something about slope? So this slope will not reach 0. We can see it's not going perfectly flat. Okay, what it will do is go close to 0. So wherever the slope is lowest, so lowest possible slope, it won't hit 0, or if it does, you have a really weird production system, but it'll go pretty low, and whatever's closest to 0 is that ideal point. So we can identify that as well with our calculus tools, which we'll get to. Okay, so that's our kind of aim here, our goal. We talked about slopes a bunch last time. I hope you can just look at these and just kind of right away say, okay, it's positive, negative, it's exactly this number for these ones. And then by extension for these ones, say, okay, positive, negative, and it's going to be bigger than this thing or less than that thing. Let's try this one here. Is this positive, negative? Okay, tell me what it's going to be between. Zero and, okay. So this is 0, this is -1. So this slope will be somewhere between that range. It's a small negative number. What about this one here? Positive, and what kind of range? Not 0 and 1. This is 0, this is 1, this is +1 here. This is the range between 0 and +1. Okay, 1 and infinity. So somewhere between 1, I know that's a really big range, but still it's kind of 1/4 of the possibility. So somewhere larger than 1 and less than infinity somewhere. So hopefully we can do that for all of these. If we can immediately recognize the red ones, then these blue ones, okay, they're going to be inside that range. Here's another way of looking at this. Trying to show you lots of different ways of thinking about it. So these two blue ones here now, that's the slope of 1, that's the slope of -1. We can add our other two kind of cardinal directions here. What slope is this? A perfectly vertical line? Undefined. It gets close to infinity as we get very close to this, but actually at perfectly vertical, undefined, and slope of 0 here. So those kind of ranges, we can say, well, these orange ones are going to be somewhere between 1 and 0 here, and then 0 and -1 down here. And then these other ones would be between 1 and positive infinity and -1 and negative infinity down here. So these kind of 4 ranges here, again, should be able to just right away identify. Seeing, okay, the exact number can be a little harder, but at the very least, this much of it. And we'll do some more practice with this today. Okay, so nonlinear functions, I'll just show you this thing one more time. So not this one, this is just linear, but all these other ones we call polynomial functions. Again, poly means many, because if we have an x squared something, kind of standard form for x squared, 1, 2, 3 parts of at least 2 things that involve x. With this one, an x cubed, 1, 2, 3 things that involve x plus a constant. X to the exponent 4 would have 4 things involving x plus a constant, and just continuing like that. Okay. So different kinds of curves. We looked at an x squared last time. We looked at an x cubed last time. And we'll look at some bigger ones today. All right, so these are the x squared, just y equals x squared. Same thing 3 times here. And let's see if we remember how to manipulate this. So if I have on the far left here an x squared graph and I do on the far left here an x squared graph and I do +3, what's going to happen? You're saying it's moving to the right? Okay, the whole thing's going to move up. The shape is the same, it's just going to shift upward. This isn't a really exact thing here. Okay, so if we subtract 3 here, then same shape, but the whole thing is just sliding downward like this. Excuse me. This one is not to the right. No. Okay. So if we have our y is equal to 3x squared, what's happening? Okay, is it kind of getting wider or is it getting narrower? Okay, let's think about the values again. So this here, 1 squared is 1, 2 squared is 4, 3 squared is 9, like this. So we're taking that result and multiplying it by 3. So 1 squared is 1 times 3. 2 squared is 4 times 3 is 12. That's already off our graph. So this is what we are getting here. Okay, so it looks, try to make sure I do this on camera. I'm not zoomed in enough. It's not really going to work. It looks like it's getting narrower, but again, mathematically what's happening is this vertical stretch. Everything is getting pulled upward. The other one here, where it's 1 over 3 times x squared. All right, this is the one where it looks like it's getting wider. And again, mathematically, what's happening is this vertical compression. If we saw a larger function, it would be a little more obvious that that is happening. And the last one, negative x squared. All right, the whole thing gets flipped upside down. That happened again. So, all right. Whole thing gets flipped upside down. That's really bad. Let's try that again. Oh, like this. Because you were saying it, what do we do to shift to the right? No? Okay. That one would be y equals x minus 3 then squared. That shifts to the right. X plus 3 shifts to the left. We're not really going to need to know this. We're not going to worry about it too much, but just that's how we do that. Okay, so these 3 basic ways of manipulating a function, especially the negative one, is going to be very important. Still review from last time. Turning points are where the function turns. So on the, how do we define this? What is happening on kind of the left side of the function here? Those are the turning points, but what is happening before and then what's happening after? Okay, so decreasing, increasing. Decreasing means we have negative slopes leading up to that point. Then at the turning point, slope is exactly 0. And then on the other side, slope becomes positive. And that is a minimum, obviously. It's a minimum point. And the other one is a maximum. We have the opposite pattern. So positive, 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 positive. Slope is 0. Negative down on the other side. So turning point, the sign of the slope is changing. And it should be intuitive to understand that the slope must be 0 here. If it's going from negative to positive, so very negative slope, less negative, slightly negative, and then slightly positive, more positive, it has to go past 0 to get to that, to make that change. We'll talk today about the difference between a local and global minimum or local or global maximum. Remember, each class got to different points. We looked at this one. So this is just a function of x cubed. And on the left side here, the right side, it goes up just like x squared. 1 cubed is 1, 2 cubed is 8. That makes sense. On the right side, sorry, on the left side here, it's going down because, for example, -1 cubed is -1. -2 cubed is -8. So 3 negatives make a negative like that. So that's why we get this down pattern here. And we talked about this as well. So I'll just review the the intervals idea. Then we're ready to talk about zeros. Okay, so you see 2 turning points here. What is this first turning point? Minimum or maximum? Maximum and a minimum. Okay, so we have 2 turning points. So how many intervals of increase or decrease do we see? 3. So we have kind of the left of the first turning point. We have an increasing slope. Between the two, we can see it's going down. That's a decreasing slope. So all negative slopes. And then after, increasing slope. So 3 of these intervals. 2 turning points produces 3 intervals. All together, 3. 2 turning points. The largest exponent here is a 3. So 3 intervals make sense. 3 minus 1, 2 turning points make sense. Lots of patterns we can notice. And then zeros. So I asked you this last time, but tell me again, what is a 0? Okay, so it's the x-intercepts. Any point where our function crosses the x-axis. If we have the graph, they're very easy to see. We just look where it crosses the x-axis. All right, formal definition of that here. So zeros are any x value that makes the whole function f of that x value, the y value, equal 0. If we have a polynomial with an x to the exponent n, whatever n is, then we have a maximum of n zeros. It could be fewer than that. It might never cross the x-axis, but maximum that many. Lots of methods of finding them. If we have a graph, it's pretty easy. We just look at the graph. We can kind of try to guess and see if we can find factors. We can use the sum product method if our a value is equal to 1. We can use the quadratic formula anywhere if we have a quadratic function, and a whole bunch more of these methods. Let's see if we can remember quadratic formula. So to show you this one more time, our standard form here, f of x equals ax squared plus bx plus c. What is the quadratic formula?
X equals to minus b plus minus square root of b squared minus 4ac over 2a.
Okay, he's got it memorized. So negative b plus minus square root of b squared. Okay, so Vincent hasn't remembered. Other people try to tell me what comes after here. AC all over 2 A, what's the operation between the b squared and the 4? Minus, there. That is the quadratic formula. So we would take, again, in standard form like this, there's the a value times x squared, there's the b value times x, there's the c, you just substitute those things in. If we do this, in most cases, how many answers, how many values will we get for x? Okay, we'll get 2 values because we have a plus minus. We have to evaluate 2 versions of this. One where we do plus and the other where we do minus there. Okay, so I hope like we've seen that before. That's kind of coming back from your high school math days. So that's one method. We have other methods as well. So let's try that. Use whatever method you want. Tell me the zeros of this thing. Go ahead. All right, so you think it's -2 and 1/3. If you're online and you have other guesses, excuse me, other guesses, other solutions, you can write them in the chat. Let's see what else we got in the chats. All right. All right, that was 2 minutes. So let's try this out. I won't go through the quadratic formula method. I'll just rewrite the quadratic formula here. -b plus minus square roots b squared or okay. So there is our quadratic formula. If you forgot that, I will recommend writing that down. But let's try another way to solve this. Let's try the factoring method. So can anyone tell me factors that they see in here? So just to write this out formally, so we're looking for the points where f of x equals 0. So that means we want 0 equal to 3x squared plus 5x minus 2. And I want to factor this to have a something x plus or minus something times another something x plus or minus something. There are factors. That's not factoring, that's just moving the 2 over. There isn't a common factor for all three terms, but we can factor into two separate things. Does anyone see one of them? Sorry, 3x plus what? Sorry, plus 2 or minus 1? Okay, so we're thinking 3x minus 1, and then what would the other one be? X plus 2, let's try that. That sounds like it's going to be close, if not correct. X plus 2. So let's try. If we think we have that correct, then if we multiply these two things together, we should get back to the original thing. So let's take these two, multiply them. So we take the first term, multiply it by each thing in the other brackets there. So that would be 3x squared. All right, that part seems okay. So 3x and then times 2 plus 6x. Then we take the other thing from the first one, multiply it by both. -1 times x minus x, -1 times 2 minus 2. And just simplify 3x squared plus 5x minus 2. It worked. So there are our factors. The method that we can use here is we look at the A value and kind of make a list of what the factors are for this. And we'd notice, okay, well, we have 3 and 1, and then we have the C value, -2, and we think of factors for that. So 2, -1, or -2, 1, and just try to multiply kind of like that and that maybe, and then add up the results and find ways to get 5. If we can find a way to get 5, that will tell us what these 1, 2, 3, coefficient here, 1 and 2, those 4 things are. So I'm not really explaining that in a whole lot of detail. If you forgot how to do this stuff, that will be something I will cover in the workshop this evening. But for the purposes of kind of our regular class, I will assume you know how to do this. This one's a bit harder because we do have this A value here of 3. If that's not there, then it's a pretty simple just sum product method that's a lot easier to do. But again, that's something I'll cover in the workshop this evening, and also some examples with quadratic formula. So let's get back to actually trying to find these zeros here. So we factored it. What does that accomplish for us?
Separate it into 2 again. So 3x minus 1 equals to 0 and x plus 2 equals to 0.
Okay, so if we have two things multiplied together and the answer is 0, at least one of these must equal 0. This thing equals 0, or this thing equals 0, or maybe both of them. So if we just rewrite that, 3x minus 1 equals 0, or x plus 2 equals 0. Then we can just do some very simple rearranging and solve for x. So 3x equals 1, x equals 1 over 3. And here, x equals -2. So there are the two zeros. These are the x-intercepts. When x is equal to 1 over 3, when x is equal to -2, that's when our function is 0. Let's just test that out here. I won't do it for both of them, but for -2. So -2 squared is +4 times 3 would be 12 plus, or -2 times 5 is -10. So -10 minus 2, 12 minus 10 minus 2, 0. So root is correct. We could do the same thing with the other one. I'll just skip that. Okay, so if we just have a function and we don't have a graph, finding zeros are a little more work, but still quite possible. Okay, let's come back to the graph stuff. So let's look at this thing here. And by the way, this is the function. 12x cubed minus x to the exponent 4. How many turning points do you see in this graph here? 3 turning points. Tell me where you think they are. But tell me the x values. So turning points, not the zeros. 9-ish. So around here, we have a turning point. -2, you see the graph turning at this point. Turning points. Okay, let's think again. What is the definition of a turning point? Okay, so the slope changes sign from positive to negative or negative to positive. If we look at this point here, we have increasing interval. So positive slopes, positive, positive, negative, negative, negative. That's a turning point. How many turning points? 1. So you might be looking at this point here and saying that looks like a turning point. What's the slope doing on the right side? It's positive. It's increasing. What's the slope doing on the left side? It's positive. It's increasing. So this is kind of a special case. It's going flat to 0, but then it keeps going up. So it doesn't actually turn. So this is a false turning point. It's not actually turning, so it doesn't count. It's just 1 turning point. And then based on that, we can see our intervals. We kind of go up, 0, and then up again, and then down. Let me erase all these little lines here. So we go up to 0, up again, and then down. So we have these 3 different intervals like this. All right, let's look at a more complicated one. Let's do everything for this one. So I'll give you some time to look at this. I want you to tell me where's the y-intercept, how many zeros approximately, what are the x values for them, how many turning points, are they minimums or maximums, are they local or global, and how many intervals of increase and decrease do you see? So take some time now and think about it, and then we'll talk about it. Okay, it's been a minute. Let's try. So y-intercept first, easiest thing. Tell me the x value of the y-intercept. 0. So there's the y-intercept, and all right, that's the x value there. Let's do color. What about these zeros? How many do you see? 5, okay. Tell me where they are. Okay, 2, -2, and just approximately. Okay, so 1, I don't know, like a 1.1 maybe. Okay, like a negative, maybe like a negative 0.25 or something. Yeah, so close to -1, but negative 0.8 maybe. Okay, so 5 zeros. Five zeros. Turning points. How many do you see? 4 turning points. Okay, so just be obvious to see. I'm going to write these as lines instead. So 1, 2, 3, 4. This first one, is this a maximum or a minimum? Maximum. Is it a local maximum or is it a global maximum? A local maximum or a global maximum? Okay, let's think about this one. So we have these 2 maximum points. This one, what do you think? Local or global? So it's a local maximum just because it's not the highest point, right? There are other points that are higher just in kind of the local immediate area. It is a maximum because the graph is going down on each side here. So that's a local maximum. Local. But what about this other maximum here? Okay, so it is higher than the other maximum that we saw here, but if we imagine, if it's a global maximum, it is the highest point on the function, of the whole function. But over here, our function goes way up to positive infinity, so not the highest overall point, so it's still just local. There's something else higher somewhere else. So this also local. All right, and the 2 minimum points that we have, are they local or global? All right, so both local because we can draw our dotted line over. All right, this is lower here. This also not the overall lowest point. Okay, so we have those 4 turning points. And then based on that, how many intervals of increase or decrease do we see? 3 increasing intervals and 2 decreasing intervals. So if we can see where the turning points are, it's pretty easy to find the interval. So we increase up to the first turning point. Let's extend that line down a bit. And then decreasing between the next 2, then increasing up, down, and up. It should be pretty easy to see that just from the slopes. All of the slopes on this first section, all clearly positive. The graph is going upward. The next slopes, all clearly negative going downward. and again for the other section. Okay, so the function that we have here, it's down here in the corner. It's an x to the exponent 5 plus minus a bunch of other stuff. So the largest exponent we see there is 5 here. So exponent is 5, 5 zeros, 5 intervals. That's kind of what we would expect, a maximum of that many. Turning points, 5 minus 1, 4 turning points. So lots of patterns and kind of connections we can notice between those exponents and how many things we will see. So that's the last part of this. The leading terms. The first, sorry, not the first term. The leading term, which is the thing that has the biggest exponent, actually can tell us a lot about the shape of the function before we even graph it. We can get a sense of what it will look like. Okay, so let's look. The one down here in the bottom right, what is the leading term for this function? So x to the exponent 5, that kind of whole thing here is the leading term. What about the one in the upper right? Okay, so this negative x to the exponent 4. The 12x cubed is first, but we don't care if it's first or second. The order doesn't matter. It's the largest exponent. That's the important thing. Two things that we can see from the leading term. First, we look at the coefficient and see, is the coefficient positive or negative? If it's positive, that means the far right side of the graph will be increasing. It will go up to positive infinity. So here, x to the exponent 5, the coefficient there, let's just write this out. So it's a positive 1x to the exponent 5. We normally don't write that extra part, but we understand it's there. It's a positive number. So we see it's going up on the far right side. And the other one here, this is a negative 1x to the exponent 4. It's negative. We see that the far right side is going down. So if we have a positive number to any exponent, it's still going to be positive. The only thing that controls if it's positive or negative the whole term is just the thing in front, the coefficient. So that part shouldn't be too surprising. So positive, right end goes up, negative, right end goes down. Second thing we can notice is with the exponent itself. If the exponent is an even number, then the two ends are going to go in the same direction. So we can see that with this thing, the top right one. So the right side is going down, and the left side also going down in the same direction here. And for the one in the bottom right, it's an odd number exponent, so the two ends go in opposite directions. I should have mentioned this. Just in case we don't know, even numbers are things like 2, 4, 6, 8, etc. Odd numbers are 1, 3, 5, 7, etc. All right, I'll just quickly explain why the exponents do that, and then we'll look at some practice examples here. So if we just imagine a very simple function like this, so y equals x squared. So if we have positive values for x, then, okay, the right side is going to be positive number squared, it's going to go up. And if we have negative numbers for x, it's squared, it's going to turn positive, so the left side will also go up. So whatever the right side is doing, the left side must do the same thing because the exponent will change the sign there. And the other type, we had an x cubed, y equals x cubed. If we have positive numbers for x on the right side, then our result is positive. If we have negative numbers, it's an odd exponent. So like 3 negatives, for example, produce a negative number. The left side has to do the opposite thing. If we had a negative exponent, then the whole thing would flip upside down, but the two ends are still going in opposite directions. Okay, so that's the last kind of thing that we can, or that I'll add here to recognize about the leading terms. So let's try that. You have 3 here. Tell me as much as you can about the leading terms for these 3 functions. Are you ready? Yeah, all right. So for this first one, tell me as much as you can about the leading term. Okay, so positive coefficient here, and you're saying, okay, so you think it's an odd exponent that must be at least 3. Okay, so let's check our information here. On the right side, going up, so must be a positive coefficient here. Also, left side is going down. We know the exponent must be an odd number. And why 3? Okay, so 2 turning points. All right, so 3 zeros. We see 3 intervals, up, down, up. Okay, so lots of clues there that our exponent is a minimum 3. It is possible to create this graph with an x to the exponent 5 or 7 and stuff, but it must be at least 3 to produce this many intervals, this many turning points, this many zeros. Okay, next one. What can we say about this? All right, so negative a, and I'll write dot, 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 x. Okay, so we see 1, 2, 3, 4, 5 zeros here. For 1, 2, 3, 4 turning points. So 5 intervals. So what do we know about the exponent? Okay, so odd exponents must be at least how big? Can we create this shape within an exponent of 3? Okay, but it can't be 3, right? So it's at least 5 or maybe something bigger. Yeah, so 3 is not possible. So, and then plus the rest of the terms to make that thing happen. Okay, and let's do the last one here. Positive a. Even numbered exponent. Okay, so the right side going up, positive, left side going in the same direction. So even number exponent. How many more? Thinking 4. Okay, how many turning points do we see? 3 turning points, 1, 2, 3. And we see 2 zeros, but yeah, so this thing here, we can see it's it's turning, but it's not actually touching. So the zeros thing, it's sort of a minimum, it's not a maximum. Minimum number of zeros, not a maximum number of zeros. How many intervals? That's more useful. 4 intervals, okay. So exponent of at least 4, of at least 4. And one more term. Again, the exponent could be bigger, but it must be at least that much. And it must be even, and it must be a positive coefficient. Just to practice the turning point thing we talked about, 3 turning points. What is this first one? So I mean like minimum, maximum, local, global. Local minimum, okay. The second one here. Local maximum. What about the third one? Global minimum, because the function does not go lower than that anywhere else. It is the absolute lowest point of that function, so global minimum. Okay, good. So those are all the things we can recognize about these functions. I know we're just looking at a graph and counting the things. It's not really that hard, but we have to be very familiar with this to understand how we have an original function, and then when we look at a derivative function, we have to be able to just visually kind of see the connections between them. We need to be very good at this to be able to do that next level. So that's why we're practicing this. Anyone have questions about these examples at all? Okay, so that is the main material for today. So we can visually, should be easy for us to visually identify zeros, maximum, minimums, intervals of increase or decrease. And then what we really did today with the leading terms is it's positive or negative, and the exponent is it even or odd, and at least how big, kind of the degree of the exponent. As I mentioned last time, everything from now on is from the pre-calculus textbook. The other intermediate algebra book doesn't cover these nonlinear functions very much. So these are the 3 sections for today's stuff. There's more detail in the book if you want to read some more. Preview question is going to be this. So this function here. So what is the function? What is f of x when x is equal to 7? And then that one's not too hard to answer. But then this, what is the function when x is very close to 7? I will show you a graph of this briefly to give you a bit more help. This is what the graph looks like, but we have something weird happening when x is equal to 7. So we'll talk about limits, which is our fancy math tool to answer this question. But for the preview, you can just take your best guess. So limits, then we can really talk about tangent lines a bit more. That will get us ready for the core idea of what we do with